we have, obviously we're excited about all the presentations. This one, as we're shifting through the time zones, now we're moving into my time zone, which is Central. And when we originally started this, each one of us was going to take our time zone. So immediately, I was going to be the crew chief. Immediately, I knew who I was going to call. I wanted Marcus Brown because he's one of my favorite presenters, top notch. If I get a chance to see him present, I'll be there. And when we got buried with everything else, I needed to find a new crew chief. And so I immediately called Joe Lance because, well, he kind of inspired this whole thing. And, he's just like Marcus, a go-to guy.
Yeah, I don't think you can think about the Central time zone without thinking about Texas, right?
Right.
And there's so much SWGN activity in Texas.
So many user groups in Texas alone.
Exactly.
My gosh.
They grew so much. When I was the SWGN rep, Texas was part of my territory.
Mm-hmm.
I had like 7 or 8 states and Texas.
Right.
They finally broke Texas out because it needs its own territory.
It really
it's
does.
that big and it's that active.
And I think everybody's in for a treat again. Joe went above and beyond. And Marcus as well. I mean, we're also talking about the reseller support, the support we're getting from certain reseller AEs. And Todd, kind of, we were talking about before, I've been in that role and I know what that's like. And I always love presenting for user groups because it's just casual and it's a little bit more fun. We said the same thing too about Andy and Jordan earlier too. They seemed like they were more laid back.
Relaxed.
It's a weekend event. It's a user group thing. We're just having fun. Yeah, we're just here having fun. So awesome. What do you think? We're ready to go to Joe and go to Marcus?
I think so.
Let's do this.
Okay, let's have it.
Let's go for it.
Welcome to Texas Region. You know how they say it. How y'all doing? Texas Region, it's so unique. They had to give us a region all to ourselves. Everything is bigger in Texas, including our hospitality. So a huge howdy and a welcome to you. Kick back, enjoy this intro. As a crew chief, I'll be back to give you more details. Hang in there. See you soon. Don't go away now.
You guys ready? Ready, set.
Wow, did you just see that? Under 7 seconds. That's impressive. But that's just a sign of what's coming your way. As I mentioned, I'll be back with you soon. Here I am, Joe Lance, your crew chief for this evening. I am president of the USUG, Houston SolidWorks User Group. I want to say good morning, good afternoon, good evening, but most of all, good day. Coming to you from Texas Region, US of A. But right now, I think our crew lead mechanic is pulling up. Let's check him out first.
And here we are once again, here with the crew lead mechanic, and I would be remiss if I didn't identify him as a certified mechanic. You know how we roll here. So with that said, I'm going to have a couple of questions for him about the vehicle that the driver is going to be using today, the presenter. So without further ado, let's hit him with some questions, see if the car is prepared. So here we are again. So I wanted to check and see really if the car was prepared and set up and it was sound. So with all the work you've put into this thing, is this car ready and can it handle it? What are your thoughts on that?
Are you kidding? That's what this car is made for. Do you think the driver could flatten the curve?
Wow, I like that. Speaking of flattening the curve, what engine is in this thing?
This one has the Flat 6 4-liter, specifically designed in Germany just for the track.
Wow, okay, so really, it's left up to the driver. Let's see if he can bring it, because we obviously know that the car can handle it. Excellent. That's exactly what I So let's really see what a Flat 6 sounds like, to see what our driver is going to be doing for us.
Before I throw it over to the driver, he's anxiously waiting for these keys. but he will have his opportunity to drive like the way he wants to and flatten things out. Heads up, I highly encourage all of the spectators to participate in the live chat to get the most out of this event. A lot of good information will be shared. I promise you, you will get just as much out of the live chat as you will from our driver this evening as he's flattening things. So engage. See you soon. Here I am once again. Told you I'd be back. You just didn't think it'd be so soon. But without further ado, our driver, Mr. Marcus Brown, who is the Content Strategist Specialist at MLC CAD Systems. And what is he going to be driving us into today? He's going to show us how to flatten anything, which we've been talking about, flattening things. Maybe he'll even show us how to flatten that flat 6 in that 911. Well, here we go. And he's off. Let's see what he got to bring for us.
Hey SOLIDWORKS user group, my name is Marcus with MLC CAD Systems. I used to be an applications engineer and now I actually do marketing. So if you ever go to the MLC CAD Systems YouTube channel and type in a friendly comment, I'm the one that generally replies to you. Today I'm going to go through my kind of big presentation that I do. I wrote this as kind of a offhanded article on our website and it blew up there. So I submitted it to SOLIDWORKS World. They accepted it. So I'm going to give it to you guys, kind of the short, quick and dirty version, because I know you guys are all experts. So we're going to go through a lot of live stuff and I'm going to talk about a lot of theory. I'm going to start with just kind of some overall basic stuff. So the agenda today, we're going to start out with some philosophy of design. Specifically, I have a two design philosophy, or it's what I call a two design philosophy. When you're flattening things with sheet metal, you have two designs. One design is the flat part, and one design is the bent part, the finished part. And those are very related, but they're not necessarily equal every single time. So we need to kind of get our heads right about those two different designs. We need to talk about the various different multiple approaches, and there are a bunch of them. And I want you to keep an eye on the end goal at all times. Our goal here is the end goal. And the time that people generally get stuck is when they say, I want to do it, but I want to do it like this, right? Thinking the ends or the methodology is more important than the ends and the means that you're using. So focus on that end goal. My name is Marcus Brown, as I said. I learned SOLIDWORKS back in 2003. I did sheet metal for guards on CNC machines, robots, things like that. Actually expanded that into medical architecture. I've done a lot of sheet metal over the years. In 2008, I was the most certified in North America technical SOLIDWORKS person. I took on the nickname CAD Ninja and then kind of switched over to the moniker of CAD Panda because the topology fits a little bit better. When you talk about flattening things, it's important to understand what might need to be flattened. Okay, sheet metal ought to be obvious. That's the first thing that comes to mind. But what about things like fiber layups, right? You're putting sheets of fiberglass or carbon fiber into a mold. Maybe you're making a label or a sticker or something that's got a form fit over another part. Maybe you're doing NC cutting. A lot of tube cutters cut as a flat shape, but they're actually cutting it on the perimeter or around the perimeter of that tube part. So you're going to cut the holes all the way around and then you're going to flatten that out and send it over to the NC machine. Sometimes you've got fab templates where you're creating something sort of really weird shaped or possibly something that's almost impossible to measure. And so you're looking for some way to transfer the design using paper or something else that tends to be flat. You start to get into things like fabric and upholstery, then you start to get into stretch, and that starts to get a little bit more complicated. Thermoforming, you don't generally actually need to flatten thermoforming. It's always just you take the thing, and I always thought thermoforming would need to be flattened, but you're always taking just a rectangular or whatever the machine takes, and then you just trim it off when you're done. So keep that in mind, that sometimes you need to flatten something, but the flat pattern is actually not important at all because the machine needs to have square stock. We also got cardboard, packaging, all kinds of stuff. The possibilities of what might need to be flattened is a pretty big list. The question then becomes, okay, why do we need an accurate flat pattern? Because a flat pattern, I'll just give you a rectangle every single time, and as long as it's a big enough rectangle, boom, there's your flat pattern, right? Just trim to fit, beat to match, beat to fit, paint to match, right? So we want accurate flat patterns so that we can avoid trimming, which doesn't always apply. Thermoforming doesn't matter. An iterative design process. If you're not, married to the design, you don't actually care about the extra time it takes to trim a prototype. So don't worry, does it really need to be that accurate? You do want to minimize your waste because you only want to make what you need. So trimming extra stuff not only is wasted energy, but it's also wasted material that you could have put into another part. You want to eliminate those extra operations. A lot of times I find that if the flat pattern isn't right, you find yourself sort of trying to dial in the bends. You want your bend locations and your flat patterns to be perfect so there's no sort of excess at the end, no remainder. You want it to look really professional. You want tight, clean corners. You want to take advantage of the ridiculous accuracy that you get on a CNC machine, right? Whether you're talking about a router, laser, plasma, whatever, you can flatten something and cut it out down to 1/1000th of an inch, generally speaking. Not necessarily repeatedly, but generally speaking, it's super accurate. And so then you can take that and use that as your assembly guides. You can make highly accurate parts, even though they need to be formed up. If you know your parts are going to be accurate, you can get the parts out the door faster. You don't have to make a bunch of extras. You can just say, yep, I need 5. I'm going to print 5. I'm going to bend 5, and it's going to be perfect because I know it is every time I've got it dialed in. Let's talk real quick about the anatomy of a sheet metal part that is a challenge to potentially work with. So what you end up with doing is you look at a part that's crazy, and you look at that part and you say, okay, I could do it a lot of different ways, but first things first, focus on the largest part of the bends. Trace the outline and use a base flange, or if it's a rolled form, draw the arc of that roll. Try to get the bend in there first, because if you build the bend with sheet metal features, it's going to be a lot easier. Now, for a really challenging part, you may have features that need to be added to the bent part, as well as parts or features that need to be added to the flat part. So in this case, I'm trying to create a perfectly oval sticker or placard or something like that. And so I create the nice roll, because I'm not going to be able to roll it very well after it is turned into an ellipse or an oval. So I create the roll, I flatten it, I cut the ellipse out, and then I flatten it out. And the flat pattern must solve. Now, you may think, okay, well, that's obvious, but for those of you that have tried it, you know that at least in the past, you had to have at least one small edge, one straight edge to roll that back out with on a flat pattern. And so what I did here is I left on my ellipse, I left the tiniest little straight edge. And that straight edge allowed it to flatten, and then I did some cleanup at the end. So that's kind of how a lot of these parts end up going. You end up working on it in multiple phases: the bent, the flattened or semi-flattened or in-process flattened, the flat part, and then anything after the flat part that needs to be applied to make that work. All right, let's talk about the rules. Sheet metal has rules, and just like rules in the real world, if you break big rules, you got big problems. If you break small rules, you probably get away with it. Nobody's going to care. And if you break enough small rules, you're probably going to be cruising for trouble. So follow the rules when possible. If you can't, I understand. SOLIDWORKS is probably going to take care of you, like we'll see here in a second. So one rule: constant thickness. In other words, if you're going to have 16 gauge sheet metal, it's got to be 16 gauge. You can't create a chamfer on one edge and sharpen it, because that creates a situation where it's not the same thickness there at the corners. So constant thickness. The exceptions being that you can create non-normal cuts and do a lot of stuff with them. Also, if you have something that's going to end up stretching, like a formed part, that's drawn out, theoretically that's going to change thickness in the real world. We're not going to calculate that. We're assuming the thickness stays constant even though you're getting a bunch of stretch. Sometimes with imported parts, the constant thickness is messed up, and sometimes with convert to sheet metal, you can't have it flat. You don't want it to be thin. You want it to be a big chunky block, and then you just convert it. Everything should be a flat and a cylinder. Now, again, that's brushed straight out the window because you can do any shape you want. But in an ideal world with a part that's just like vanilla sheet metal, everything is a flat face or a cylindrical face. That's what a CNC sheet metal bender will do. You can do lofts, you can do sweeps, you can do flexible materials that you know are it's going to go all crazy, surface flattened. There's exceptions galore, but those tend to fall into some of the categories. You can't apply bends to bends I don't know, 2020. They've changed this. It used to be, if you're on an older version, this does apply. It used to be an arc touching another arc with no straight in the middle would be a problem. Or even worse, an arc that then just took off in another direction. That's a bend on top of a bend that's going to get added on top of another bend. It just gets crazy. SolidWorks is like, you know what, I'll just take care of that for you. So if you've ever run into a problem in the past where your lofted bend or your swept bend or something like that didn't flatten, it probably does now with no problem. It's just boom, automatic. You can't have parts that are overlapped. Like for instance, when they bend, if the parts are overlapping or intersecting, it can't physically happen, and it can't intersect in the flat. But there are times when, for whatever reason, you need to cheat, and SolidWorks generally is okay with you cheating. It generally gives you ridiculous, impossible things and lets you decide, is that something that I can accommodate through other means, right? Through stitching sheets together to create a flat that's impossible from a single sheet, but maybe it's from multiple sheets. Or maybe you've got two parts that need to touch because they're going to get spot welded or something like that together. Generally, that's going to work out fine, but just keep in mind, if you can keep a small gap in there, you're going to be better off. The part needs to be manufacturable, and of course, this is all sort of just up to you because you're the one that's stuck with it if you can't manufacture it. But there are some really cool tools out there where you can create, completely enclosed cubes, for example. I mean, if you're making it out of a piece of paper or cardboard, then you can bend anything, right? So the last one, you need to have a flat face or a flat edge, and that's because the flat pattern feature at the bottom of the feature tree has to have something to say this is the fixed edge or fixed face. It's got to flatten relative to some fixed object. So make sure you have a flat face or flat edge. That one's a pretty good one, although keep in mind, kind of like with that elliptical label example I did just a second ago, you can have a flat edge that exists in the flat pattern but then gets sort of trimmed or eliminated after the flat pattern in a post feature. Okay? This is required knowledge. You need to understand bend allowance, bend deduction, K-factor, etc. Generally speaking, when you go and talk to the guy that runs your brakes, the guy that runs your lasers, the guy that, everybody that works with sheet metal, and you ask them, explain to me what bend allowance is versus bend deduction and why would I use one or the other, you will get a different answer from every single person you talk to. The the thing of it is, bend allowance, bend deduction, those are old school AutoCAD 2D, like rules of thumb. They work really well, but they were based off of the same dies on the same material, and if you have a different bend angle or a different bend radius or a different die set or a different humidity in the air, it's going to stretch a different amount. So and you'd have to manually keep track of this all. So I don't recommend using anything but K-factor, just for simplicity's sake. I'm lazy and you should be too. So K-factor is usually 0.3 to 0.5, and the idea is K-factor is the percentage through the thickness that you're not getting either compression or expansion in the material. When you bend, it's compressing on the inside, expanding on the outside. Somewhere along there is a neutral line. If it's perfect, then that neutral line is halfway through, exactly halfway through, and that's a 0.5 K-factor, which is the default SOLIDWORKS value. If the material has a tighter bend, if it's a thicker material, you'll start to see it drop lower down to about a 0.4, 0.35, 0.3 on the max side. And a good rule of thumb is if the bend radius is very small or the material is really thick, then you're going to have to find out where that's at. But if the material is pretty thin, and paper or thin sheet metal definitely fits into this, or if the bend radius is equal to 3 times the thickness, then you can just use a K-factor of 0.5 and you're good. And a lot of times I find that people will have a set of dies set up that follows that rule that just automatically gives them a K-factor of 0.5. It's perfect. So if you don't know what your K-factor is, make a plate, a 2-inch by 2-inch plate, apply a 90-degree bend to it in SOLIDWORKS, and then go cut a 2-inch by 2-inch plate really accurately, bend it, and sit there and measure it. And what you need to do is adjust your K-factor until the measurements you get on your sample part match what SOLIDWORKS is calculating. It also helps to understand which direction you're solving for, because depending on what direction you're solving for, that's going to be where that K-factor applies. So for example, let's say you're doing a rolled cylinder, you know what the diameter of that rolled cylinder needs to be, you know the folded part. You design it in SOLIDWORKS, you solve for the flat. If you adjust the K-factor, that tube will not change size, but the flat will. It'll get longer or it'll get shorter. Now if you know what the flat needs to be, such as you want to cut a round hole because you're using a punch, but then you're going to roll it up and you want to see what the shape is, you'll build it in the flat and then you'll roll it up. In that case, the K-factor is applied to the folded part. You always have to start with one or the other, and in fact you can mix and match, but every feature has a design intent. The K-factor is translating from one design to the other. And what do I mean by one design to the other? I mean you've got 2 designs. You've got the flat and the folded. And they are differ by, theoretically, a K-factor, and that's it. But in the reality, sometimes you got to get more creative than that. So let's do some examples. Let's start with just some regular sheet metal features. Just do something fun here. So I'm going to go ahead and create a new part. Real simple. And when I do a new part like this, especially in sheet metal, I like to just kind of try to get as many of the bends in there as I can initially. Then let's just create a weird shape. And we'll come up here to sheet metal and do a base flange. Then when you're doing sheet metal, you're almost always either going to be right on or you're going to be off by a thickness or 2. Because if you're not paying attention to the thickness being to the inside or the outside, classic design intent mistake, you're going to have problems. So we're not focusing too much upon the sheet metal specifically, but if I come in here and I draw open profile and I do a base flange, it creates a sheet metal part. And as long as you just kind of periodically check, yep, it can be flattened, you're good to go. All right? Now keep in mind, remember I said you had to have a face, a flat face or a flat edge? That's because this flat pattern feature here specifies where it's flattening from, and that stays put. So if you ever decide, no, I want this to stay put and everything flattens relative to that, right? You can do that. I kind of liked it the other way. I'll switch it back real quick because that one seems to be more convenient. But if you ever have your flat pattern off at some weird, crazy angle, pick one that's sort of square with the world. You got a bunch of other features, and as long as you do something in sheet metal and SOLIDWORKS says it's a valid sheet metal feature, you should be good to go, right? So like here's an edge flange, and I'm just going to kind of come in here and modify this a little bit to make it, you know, line up here. That looks pretty good. This one actually blew up, probably because I tried to overlap. And remember what we talked about, you cannot have overlapping parts or touching faces. So we'll make this where it's not so mad. And I've got auto rotate normal turned on because this is a brand new install. We'll tolerate that. Okay, so there's an edge flange. It flattens, right? No big deal. You've also got miter flange. If you do a miter flange, here's a little tip. Grab the edge you want the miter flange to start at, near the edge where you want to draw it, then hit the miter flange command. Oh, actually, you got to do it the other way around. Do the miter flange command, then click the edge. It creates a plane with the origin at the point, and then as long as your profile is attached to that origin of that sketch, you're going to be good to go. So I'll just do one of these little dudes and click OK. Just kind of freestyling here, and propagate tangency goes through and does a nice job of taking that shape and creating a whole bunch of ends really quickly. Again, let's check and make sure. Yep, flattens no problem, other than that's interesting. So that guy's giving me trouble. Let me try one more time real quick. I'm going to just turn that back to vertical and see what that looks like, because I don't really want to create a problem that later on is going to bite me, because I'm going to do some weird stuff. All right, next thing I want to do is I want to create a cut. And this is one of my favorite sort of tips, shortcuts, whatever, with the new plane feature back in, I don't know, 08. You create a plane, actually probably wasn't 18, it was probably 18, but pick a couple faces, create a plane, it creates your symmetry. It back calculates a symmetry plane, which happens to be a perfect 45 on two normal faces. All right, I want to run a pipe through all these faces in the sheet metal, right? I mean, it's a pretty common thing. Sheet metal has some like hose, some structural pipe or something like that going right through it. So I run this cut all the way through, all in both. And it by default, it turns on normal cut. And normal cut, what we mean by that is it's going to cut a straight cut normal to the surface, so that when you flatten it over here, you got nice, clean, straight cuts and everything's fine. Okay? If you want that to have sharp edges, you can turn off the normal cut, but you're going to break a rule. So if you're using an old version of SOLIDWORKS, this is now going to hate you. But check it out, it's got a really sharp edge right there. It's going to slice your finger while you're holding the part, unless you deburr it. But it'll still flatten. Yep, don't call me a liar, SOLIDWORKS. You break enough rules and SOLIDWORKS gets a little touchy. But you break a couple rules and generally SOLIDWORKS is going to totally be fine with it. All right, so that's looking pretty good. At this point, you kind of get the idea, right? If you start with sheet metal features, you stay with sheet metal features, you should be fine. It's going to work out. That's the easiest thing you can possibly do. Insert bends is a really great way to take a part that's theoretically already sheet metal and add sheet metal features. So if you've got a bunch of old Pro E, sheet metal parts, step files, you got an old, AutoCAD 3D parts, whatever, insert bends is absolutely the way to go. All right, does have to have flat or cylindrical faces. It doesn't have to have bends. If it has bends, it'll capture them accurately. If it doesn't have bends, if the corners are square, it'll add your defined radius in the bend. So for this one, I'm going to go ahead and open up a real quick. I got a part on my desktop here that I created earlier. I had another example on this and I couldn't find it, but this is an imported step file, and it's just a dumb, for lack of a better word, dumb solid. But if you say insert bends and you pick a flat face, Bob's your uncle, you've got a sheet metal part with intelligence. Pretty awesome, right? That right there is brilliant, and you should always use insert bends whenever you can if it's an imported model. Don't use convert to sheet metal. I'll show you that in a second. That's for other things. But insert bends, man, super stupid simple. Great. Convert to sheet metal. Now this is one that has really grown over the years. It's constantly been improving. The corners are better. The error handling is better. The ability to handle arcs on arcs on arcs, all better. So this presentation has had to adapt over the years with the improvement in the software. But basically, if you've got something stupid or complex, like the classic example is a hopper, and you need to reverse engineer it, or wrap it in sheet metal, or create it out of sheet metal, this is, sort of the way to go. And so for this one, just to kind of show you what I would do, I like to just create a really stupid shape. I'm going to add some draft to it. And then I'm going to just chop it with, I know. Let's draw a circle. Yeah, this is a terrible idea. We'll see how this works. All right, I want to make a sheet metal part that is this guy right here. Right? I want to make a sheet metal housing that is that random drafted cut shape. Convert to sheet metal is your perfect way to do that. And what it does is you say convert to sheet metal, pick a flat face, and then anywhere you grab an edge, it's just going to convert that edge. And if you kind of pick in a weird order, it'll actually flatten in a weird order. So like this one right here, look at that one. If I flatten it, you can see it flattens out, but it actually created bends here, and then it sort of wrapped around the side. So depending on how you grab them will determine how that works. Now for this one, I can't possibly make this whole thing out of one piece. If you need to create it out of multiple pieces, check the Keep Body button, and then you can just come in here and convert it again. So let's do this one, grab this edge right here, this edge right here. Now I'm sure this is not going to work. Yep, coplanar. But let's check this guy. Check that bad boy out. Right? I wonder if this will do it. Nope, doesn't like that one either. So we'll have to come in and figure something out later. But there is a couple of sheet metal parts, very quickly created. And the beauty of it is, any changes to the geometry and these flat patterns are going to update right away. Right? Change the draft, angle, whatever. Right? Looks like I'm blowing stuff up right and left. That's what you get with a live demo, but hopefully it's enjoyable. So just make sure that it can be flattened. A lot of times you'll see these where they overlap each other. That's on you. You're going to have to fix that. Lofted bends. This is a really good one. The main thing to keep in mind with lofted bends is that you cannot create guide curves. It's a loft with no guide curves. Now, a lot of times people have a flipped orientation of parts. So like this auger. If I was building this auger in a sheet metal, or a surface part, I would use a helix as my pattern, my path, my curve, right? you can't use that. It has to be straight. But if you think about it, if you use helixes as your profiles, then they are straight across to the other side. Let's make one real quick, because this is a fun one. You basically just start a sketch. Let's do like a 1-inch hub on this guy. We'll do the first one first. And we'll go in here and say helix. And we want to do a 2-inch, no, let's do a 3-inch pitch, 1 revolution, start at 0 degrees. Looks good. Now we'll do another one, start a sketch, draw my circle, and we'll do this with like a 4-inch OD. So we're wrapping a 4-inch auger around a 1-inch post. Again, we'll do a helix, same pitch, starting revolution, everything like that. You cannot create sheet metal lofted bend from a curve. So you got to do a couple additional quick steps. You got to create a 3D sketch for each one and convert it. There's 1. Here's 2. I find it's useful to hide my helix, otherwise you're going to accidentally grab it. The sheet metal's going to get mad. But there is a loft where those would have normally been my guide curves. I can now lofted bend from one to the other, from here to here. Now this is going to be a formed part. You cannot approximate this on a brake press, no matter how good you are with the brake press. That ain't going to work, right? You're gonna end up forming this with a hammer or something. But it does a nice job and it flattens with no problem, right? Makes quick work of building an auger. If you need to do one where it's going to be approximated by a brake press, that's where you're going to have kind of that more classic, you know, squared around. Or what's more likely or more common is maybe half a squared around. So you're doing like a, let's do kind of a weird shape there. And then we'll go to like an arc here. Center point arc. Do. Right? Lofted bend from there to there. This one can theoretically be approximated on a brake press, just like that. And so if you have something that can be approximated using straight lines, you're good to go. This used to be so much harder. You had to do straight line to straight line. They had to be parallel. They had to be connected. Now it's just so easy. This presentation has gotten so much easier. I used to be always the stump the chump guy on support. Somebody's got something they can't flatten. They're like, hey, Marcus, you try to flatten this? I'm like, yeah. My job's so much easier these days. So that's looking pretty good. Make sure it flattens. Looks good. Feeling good. Man, SOLIDWORKS is just crushing it right now. Now we're getting into the really weird stuff. So lofted bend used to be like the only thing you could do that was non-flat or cylindrical. Then you got into the lofted bends. Now you can do a swept flange. That's where you're going to get things like donut shapes and stuff like that. It's an open profile and an open profile, and you sweep it. The only thing is you want to keep an eye on how you're flattening it. So are you flattening it along the path, like it's going to be rolled like seamless guttering from a straight, strip? Or are you sort of flattening it from the side and sort of bending flanges down to form those shapes? Those are the two. I've been having problems. I haven't looked at it again in a while. Problems with some of the flattening on that. So it's a little bit weird, but you can get some pretty complex stuff there. Again, you may have to flip your perspective, right? If you think, okay, well, I can't do it that way because it's not a single profile. What if you, do it from the side, do it sideways? Surface flatten. Right now we're getting really weird. Because surface flatten is a situation where it's not sheet metal, right? The auger is technically it's not sheet metal because you can't bend it on a brake press, but that depends on how you define what is sheet metal. You can do things that are non-planar, like drawing of metal. But surface flatten is when you really start to get some really crazy stuff going. It's about the most powerful thing you can do in SolidWorks when it comes to flattening things. I was doing a sheet metal training class one day, and I said, I bet I could flatten everything. And it's kind of the genesis of this presentation. And somebody said, can you flatten an orange peel? And I said, what shape, right? Do you want it like a flower? Do you want it peeled in a helix? And he said, I want a helix. And so I did. And the different ways that you can do this vary because some of these get a little bit complicated. But let me roll this back here. Here's one way that works probably better than the surfacing, because the surfacing can get a little bit difficult. But you just create any shape you want. And then you just go in and you cut it with like a thin rectangular cut. And in this case, I just did it as a swept cut on a helix. And just cut everywhere I wanted it to peel away, which is where the cuts would actually be, and then surface flatten. And it just flattens it. And up on our social media for MLC CAD Systems, I've got a picture of an apple peel that my wife did because she knew I did this presentation, so she peeled it in a spiral, and it looks exactly like this. I mean, it's every time it looks this way, and you can predict it with some really great accuracy how it works. To show you that last step, because preparation to here can get a little bit crazy, but once you get to the point where you have something that can be flattened, you just come in and grab the surface flatten command, and I usually have that on my toolbar. Surface flatten. Let me add that here. And you just pick the face you want to flatten, and then pick where you want to flatten it from. You have to start from a point of some kind. And so depending on where you pick that point, that might determine just exactly how it does it. But it's almost doing FVA on this thing. It just meshes it, and then it does it. You can adjust the accuracy, you can add relief cuts, but there you go. The only other thing that's worth looking at is that you can right click and turn on the deformation plot. This is where you're going to start to see it either wrinkling or tearing because there's tension or compression. So this one has a lot of stretch right there at the top, and if you've ever tried to peel right down to that nub, that stem, you know that right inside there is a lot of stretch going on because it's sort of being turned inside out. Then you get a little bit of compression depending on how thick you make the peel. I've got another one of these that I did, another approach using surfacing, but a couple of years ago that kind of broke it. Surfacing, you just got to make sure that the surfaces are not overlapping, so you typically need to cut a little hole in the middle where you don't need to worry about that on a solid. But then as long as you can trim the features, you should be good to go. Now this one, if it's anything like it was in 2020, I would go in there and I would try to do that and it would actually break. But in this case, this one's a little different. I do the surface revolve, right? And then I come in and I do my sweep. And then I do some split lines at the intersection. I copy the body so that I have two very close nearby surfaces. Then I trim them. You end up with like 18 features to get this done. It takes way too much time. The solid one I did as a workaround, found out it worked a whole lot better. I was trying to be cute with surfaces. Which brings me to sort of the bottom of the bucket, the bottom of the barrel. when you can't do it another way, when you can't flatten it using one of those features, you gotta cheat. And as far as I'm concerned, cheating is totally acceptable. So for example, here's an example where this is this was on like a crimp connector where a little window was being bent out along the cylindrical face. Now remember when I said that sheet metal needs to be flat faces and cylinders? Well, if you put a bend on a bend, normal to a bend, it creates this toroid donut shape, and that's just a no-go. You can't put bends on bends. They're constantly making it better, so they're going to make me a liar here in a couple years, but this is just a no-go. But the trick with this one is you don't need to know what the flat and the bent parts look like. You actually already know that. So why worry about SOLIDWORKS figuring it out when you can just tell SOLIDWORKS? So in this one, I did this one ahead of time because I didn't want to have to sit there and try to recreate it. But basically what you're doing, and I'll show you my feature tree, right? There is my bent part, and here is my flat part. And you're thinking, wow, that seems really simple. Bent part, flat part, right? Well, the bent part, I had to do a loft to get this bend region, because you can see it's a bend that's bending, a bending bend. You can't bend bends in sheet metal. I had to do knits and surface thickens and all this other stuff just to get the shape right. And the shape's not perfect because I probably need to come in and like curve the edge here or something like that. But once you get the tooling and the machine that actually does this, you'll know what those measurements are and you can trim it up and make it look realistic. But I had to build that geometry completely. And once I got that completely done, I switched my configuration. And SOLIDWORKS always creates that default sheet metal flat pattern sub configuration. So why not just save it the trouble, create your own configuration called flat, throw away all that nonsense. I just suppressed it and created the geometry that I knew I wanted. Now, is that cheating? Yeah, of course it's cheating. Does it get me my print? Yes, it gets me a perfect print. This print says this is what the flat pattern needs to look like. This is what it looks like when it's bent. Any questions, right? If you've got a feature like that where it's a bend on a bend or something like that, something really impossible, you're probably going to take the route of cheating. And that's fine. It's all good. The end result is what matters. One more note about cheating though, and it's not necessarily cheating, but it's an awesome workaround. In this case, I did a surface body. I did surface modeling to create that shape, and then I thickened it. If you find yourself struggling with a part that's not actually constant thickness, maybe it's a wavy sheet and you want to flatten it, but it's you know, it wasn't modeled correctly, so it's not constant thickness, and SOLIDWORKS is bonking on it for some reason. Convert it to a surface. Take one surface face, knit it, right, or offset it 0 thickness or whatever, and then thicken it back up again. It's like an instant uniform thickness routine. Super, super cool. All right. In addition to the cheating, you do have other options you can explore. I'm not going to promote or endorse any third-party products, but there are products out there that have the ability to do more advanced, you know, especially drawing, stamping operations, things like that. There are better ways to do that. I would not recommend doing progressive die stamping in sheet metal. Can you get by? Yes, but is that your best way to do it? No. Like I said, those surfacing workarounds are great because not only do you have the power of surface, but then you can do the surface flatten, or you can thicken it and then try to insert bends that way. So hopefully this was helpful. I hope you learned something. I hope you kind of squared your brain as far as how to flatten things. Keep in mind, there's never going to be 100% everything can be flattened, especially if you go to the surface flatten, that's like cheating, right? You may not also need a perfectly flat pattern. You may have to sort of start with a rectangle, bend it up or form it or draw it or whatever you're going to do, and then cut off the excess and then measure the excess and sort of reverse engineer it that way, right? However you do it, I hope you do it. Have fun with it. We're going to hang out here for questions.
Wow. And I'm back at you one more time to just say amazing job, Brown. Marcus, excellent job. I hope you all was blown away as I was. He just amazing to flatten everything inside. Truly amazing job. We'll definitely have to let the crew chief know that you were able to flatten that curve. You did it. That's what I'm talking about. And with that said, we're out of here. I'm gonna throw it back to the broadcasting team. Guys, we're done. See ya. Thank you all.